Okay, so here's my solution to the problem that we did on buoyancy. And the problem had a 1 kilogram mass suspended from a spring scale, and the scale read 8.5 newtons. Now we can tell right away that something else must be going on here because a 1 kilogram mass weighs 10 newtons, and indeed it was suspended in water. Okay, so we might think about a couple of things here. And let's start with just defining what the force of buoyancy is. The force of buoyancy is equal to the mass of the water displaced times g. That's the weight of the water displaced, and that's what we mean by the buoyant force. So in this case, it would be the density of water times the volume of the object times g. Okay, now let's do our free body diagram. So we have gravity downward and two forces upward. We have the spring scale and buoyancy upward and gravity down. The sum of the forces is therefore the spring scale up, 8.5 newtons, minus, plus, the buoyant force is also up, rho v g, and gravity is down. And because it's not moving, this is 0. Okay, so we can solve that now, and what this means is that rho Vg must be 1.5 newtons. I'll just do that subtraction and put them on the other side. The density of water is 1,000 kilograms per meter cubed. Notice that this is the fluid, right? It's not the density of the object, but it's the density we used to calculate the mass of the water that is displaced. Okay, so, well, we can just solve then. The volume of the object is 1.5 newtons divided by 1,000 kilograms per meter cubed, 10 meters per second squared. This is 1.5, and I noticed that the kilogram and the meter per second squared is the same thing as a newton. So it's 1.5, let's see, 10 to the 1, 2, 3, 4, times 10 to the minus 4 cubic meters. And that's the answer.